Welcome to the Explainer. All right, let's just jump right in. Think about it. Our world is creating this absolute tsunami of data every single second. We're talking clicks, sensor readings, social media posts, you name it. So today, we're going to tackle a huge challenge. How do we actually capture all of that?
And that question, that's really the heart of a process called data ingestion. It is the very first step in any big data pipeline, and you could argue it's the most critical one. I mean, it's all about solving that puzzle. How do you get data from point A, where it's born, to point B, where you can actually store it and figure out what it means?
But before we get into the clever solutions, we really have to wrap our heads around the size of the problem we're dealing with. Because this isn't as simple as, dragging and dropping a file from one folder to another. Not even close.
So, engineers are up against what they call the 3 V's. First up, you've got volume, and we are talking an enormous scale of data. Then there's velocity. This stuff isn't just sitting there, it's flying at you at incredible speeds. And finally, variety. It's not all neat and tidy. You've got structured data, messy text, images, videos, the whole shebang. Put it all together, and you've got a whole lot of uncertainty to manage.
Okay, so you might be thinking, why get so complicated? Why can't we just use the simple methods that have worked for years? Like, why not just point that data fire hose directly at our database and call it a day? Well, it turns out that's a recipe for absolute disaster. Let's see why.
Back in the good old days, the most obvious thing to do was just create a direct connection. You'd have your data source, maybe a web server, and it would just write straight to your database. Simple, right? Seems logical. But that simple design, it's just way too fragile for the world we live in now. Here's the problem. Imagine a single viral post or a sudden spike from a bunch of sensors. That tidal wave of data hits your database all at once, and it just gets completely overwhelmed. Databases, they're just not built for that kind of super fast, unpredictable writing. And what happens? Best case, you start dropping data. Worst case, the whole system just goes down. Poof! So to handle all that chaos, modern systems have a much, much smarter design. Instead of that fragile, direct connection, they build an architecture around 2 core ideas that create a kind of buffer zone. The first piece of the puzzle is something called a message queue. And honestly, the best way to think about it is as a shock absorber for your data. It sits right in the middle and acts as a buffer. It basically separates the wild, unpredictable flood of data coming in from the nice, steady pace your system can actually process it at. It just smooths out all those crazy spikes. So here's how that plays out. On one side, you've got a producer. That's your data source. It can just throw data into the queue as fast as it can possibly generate it. The data just waits there. Then on the other side, you have a consumer, say your database, and it just pulls data out of the queue whenever it's ready at its own comfortable speed. This whole idea is called decoupling, and it's brilliant. The producer and the consumer don't even have to know each other exist, let alone worry about how fast the other one is going.
Okay, so the second big idea is a super flexible pattern called publish, subscribe, or PubSub for short. And this is where things get really cool, because it means the person or system sending the data doesn't need to have any clue who's going to end up receiving it.
The classic analogy here is a magazine subscription. Think about it. A writer, the publisher, just writes an article and sends it to a topic. Let's call it tech news. They don't have a list of who to send it to. Then anyone who's interested, the subscribers, just raises their hand and says, "Hey, I want the tech news," and they automatically get a copy. The best part? You can add 1 million new subscribers tomorrow and the writer doesn't have to change a single thing they're doing.
All right, so these are great ideas, right? Message queues, PubSub, but how does this stuff actually work in the real world? Let's talk about the actual tools engineers use, because these aren't just textbook concepts. They're the engines behind some of the biggest data platforms on the planet.
And we're going to look at 2 of the heavy hitters that really embody these principles. On one end of the spectrum, you've got MQTT. Think of it as lightweight, fast, and nimble. And on the complete other end, you have Apache Kafka, which is the industrial-strength, enterprise-grade beast built for absolutely massive scale.
To really get MQTT, you just have to hear its origin story. It was created way back in 1999, and not for some big tech company. It was built to monitor an oil pipeline running through a desert. The problem was, how do you get tiny bits of data, reliably, from sensors where you have almost no bandwidth and very little power? That's what it was designed to solve.
And that heritage, that's exactly why it's a perfect fit for the Internet of Things, or IoT, today. You can have a tiny little temperature sensor publish its reading to a central hub, called a broker,
And then any device that cares about that temperature, whether it's your phone or a server, gets the update instantly. It's just crazy efficient.
Okay, now let's pivot to Kafka. This thing was born out of a totally different universe. It wasn't a desert pipeline, it was developed inside LinkedIn. Their problem was trying to manage the absolutely immense, never-ending river of data flowing through the company. We're talking every single click, every profile view, every new connection, all of it.
So its architecture is all about two things: massive throughput and rock-solid reliability. A Kafka cluster really becomes the central nervous system for a company's data. You can have hundreds of different systems all pouring data in, and at the same time, hundreds of other applications are reading that data for totally different reasons. And the magic is, they don't get in each other's way.
But here's the secret to why Kafka is so dominant. It's not just a message pipe. It's really three incredibly powerful things rolled into one. First, yeah, it's a messaging system. But it's also a storage system. It can safely and reliably store petabytes of data for as long as you want. And it's a stream processor, meaning it can actually analyze and react to data in real time as it's flying through the system.
Okay, so we've gone through all these concepts, these different tools. What's the big takeaway? Why does any of this matter? Why bother with all this complexity?
And here's the bottom line. Data ingestion is not just about moving stuff from point A to point B. It's about taming chaos. And you do that by picking the right tool for the job. You grab a lightweight, precise tool like MQTT when you're working with millions of tiny sensors. But you bring out the industrial-strength sledgehammer, Kafka, when you're building the data backbone for a huge company.
At the end of the day, that's what these modern architectures do. These message queues, these pub subsystems, they create this essential, resilient buffer. They're the shield that stands between the messy, unpredictable real world and the finely tuned systems that have to make sense of all that chaos.
And that leaves us with one final question to chew on. We've seen how these tools grew up to handle the first big data explosion. But our world is only getting more connected. We're generating more data, faster than ever before. So what's next? How will these tools have to change and evolve to handle the next great data flood?